We talked about boosting, and we saw some examples of how to use boosting with trees and stumps and alternating decision trees. And now we're going to talk about one of the most interesting and mysterious aspects of boosting, which is that it tends not to overfit. And that is something that has been confusing a lot of people and is still, I can say, something that is not in complete understanding. So here is the phenomena. Here is an example of using boosting on top of decision trees. And what I'm plotting here is on the vertical axis, it's the error. And on the horizontal axis, it's the number of iterations of boosting, so number of trees that were combined. Okay? And note that the scale here is logarithmic. So what do we see initially? What we see initially is that the error, the training error, is basically increasing a little bit first, and that, if you think about it, is quite possible because you just have, let's say, two rules, and so the stronger, the one that has a bigger alpha wins, and maybe the one that has a bigger alpha is actually not as good. And then after 5 iterations, you get training error of 0. So the training error gets to 0. And the test error, meanwhile, went from 18% to something like 9%. Okay? So that is good, and that's basically what we expect to see. But if you actually observe the boosting algorithm itself, there is no reason to stop here, right? We got training error 0, but the only thing that will stop the boosting algorithm in its tracks is if it gets a weak rule that is perfect. Right? If the weak rule is perfect, then basically you're dividing by 0 and you can't continue. But as long as the weak rules are not perfect, you can go on. Okay, so in this experiment, we went on, and what you see is that, of course, the training error cannot change because it's already 0. And the test error actually continues to decrease in a very significant way. Okay? So what you have here is a decrease from this error of about 9 here to an error of about 3%. And as I said before, this is for 10 trees, 100 trees, and 1,000 trees. So this is very different from what we expect usually from doing machine learning with models that have more and more parameters. What we expect is that after we reach training error 0, then the test error will start to increase because we're overfitting. But here, what we see is that, to the contrary, actually boosting continues to improve the test error after the training error is already 0. So what this means at a high level is that we're using just about 10,000 training examples, that's the size of this training set, and we're fitting these 1,000 trees that together have about 2 million parameters. So how can you ever fit 2 million parameters using just 10,000 trees, right? I mean, what you expect is that the curse of dimensionality will completely destroy your predictive ability. But that doesn't happen. So to explain why this is going on, let's think again about the margins that we talked about a few videos ago. So here we have our examples, and the horizontal axis is the margin. And what we see here is that all of the examples are to the right of the 0. So all of the examples suffer error 0. And in a sense, in terms of this 0-1 loss, we're done, right? There's nothing more that we can do. But the loss function that boosting is minimizing is this exponential function. It's not this one. And therefore, it's basically just going to increase, it's going to push these examples further to the right. So later they will be something like this. And what we have here is that we have no examples with small margin. Okay, so even though the training error didn't change, the distribution of the margin did change in a significant way. And that, we're claiming, is the reason that we're getting better performance on the test data. So, let's think about it again. If we have the loss function here that we're trying to minimize, we're bounding it by this exponential function, but we might be bounding it by something else, like hinge loss is basically this kind of loss, and that has to do with the error of support vector machines. So soft support vector machines use this kind of error. And then you have logit boost that minimizes a slightly different function, and then Brown boost, which is another algorithm that I invented, which has yet another kind of loss function. But all of these loss functions, they try to push examples not just to cross zero, but to be further away from zero. And here is the experimental evidence that this is actually happening. Okay, so what we have here is the margin theta. Actually, we have something we call the normalized margin. So this is a margin divided by the sum of the absolute values of all of the alpha weights. And so that number is between -1 and 1. And now what we're looking at is the cumulative distribution of the margins of the training examples as a function of which iterations we're in. So if we look at iteration number 5, we see that all of the examples are to the right of 0. Okay, so basically that is consistent with what we know, which is that at iteration 5, all of the training examples are correct. But then if we go to iteration 100 or 1000, we see that these examples around here were pushed to have a margin that is above 0.5. And what we paid for it is that some examples that had margin 1, meaning that all of the rules were correct on them, they actually got slightly smaller margin. Okay, so this is consistent with what we were saying, that after 5 examples, the training error doesn't go down, but the margin distribution changes, and the minimal margin that you have is larger. So that is associated with having smaller test error. And what you see here is that after 100 iterations, you have the line, and after 1,000 iterations, you have the dotted line. And so there's almost no change. So even though we added 900 trees, we actually were just standing in place, where it didn't really change our prediction by very much. So this was actually proven by Rob, me, and Peter Bartlett, and Wei-Sun Lee. And we have a general theorem that says that this is not just something that we can observe empirically, but it has theoretical explanations. So what we're talking about here is convex combinations of some kind of base functions. Okay, so we have basis functions that we're using. That's the weak rules. And we are taking a convex combination of them. We're not here concerned about how we're finding the convex combination. We're just interested in what is the difference between the training error and the test error. So what we have shown is that the probability of making a mistake with this rule, with the rule F on the true distribution, is bounded by 2 terms. One term is the fraction of the training examples whose margin is smaller than theta. Okay, so that's where we said, okay, we don't have any examples with margins smaller than 0.5. And then we have a term that depends just on theta and on some other parameters which are not critical at this point. So these are the size of the training sample and the VC dimension, and then the theta. Okay, but the important thing, the thing that explains basically the experiments, is that there is no dependence on the number of weak rules that are combined, right? So when we say that this has 2 million parameters, this is really not so important, because the important thing is how much of a margin we can get, and the number of parameters can be ignored. Okay, so that basically says there's no dependence here on the number of parameters, as long as you have a significant margin. And if you know something about support vector machines, there are very similar theorems in that case too. So this suggests an optimization problem. The optimization problem looks something like this. Let's suppose we have our data that has some margin, and then we want to maximize the margin, because we want the 1 over theta to be small, but we also want to have a small number of examples that are below the margin. Okay, so this is a combined problem of where we have the number of examples that are below theta, and then we're trying to make theta as big as possible. So this problem, unfortunately, is at least as hard as finding the best combination, the combination that minimizes the number of mistakes, and that problem is NP hard. So we really don't know how to do this in any effective way. So what I want to talk about now is a little bit of the idea of the proof. It's not the formal proof. For that, you'll have to go to the paper. But the idea of the proof is actually quite intuitive and simple. So suppose that we have now positive and negative examples, or male and female, that are in this plane, and they're separated by this line over here, and but not perfectly. Like here, there's an example that is not separated, and here are examples. So we have this separator that has some small number of mistakes, but we have this other property that we have a large margin. So we can basically, none of the examples gets too close to the separating line here, and that we claim is useful for the amount of test error that you would get. So why is that? Basically, it is because if you look at the possibilities of wiggling basically this plane or this line, we see that you can wiggle it quite a lot and not really change the training error. Okay, so we have a lot of room to wiggle things, and because of that, we're going to be more confident about our predictions. So why are we going to be confident? It basically boils down to looking at different examples and at our confidence level. So if we have examples here that are pretty far from all of these hyperplanes that are good, then they are unlikely to change prediction if we have some kind of alteration to the training set. Like, for instance, suppose we just sampled a new training set from the same distribution, we're likely to get one of these hyperplanes as being the best rule, and this best rule will agree, all of these best rules will agree on the predictions here. And similarly, if you have examples here, okay? So examples that are far from the margin, you're very confident about them because you know that if you even change your classifier a little bit, it's not going to change your prediction on those examples. On the other hand, if you have examples that fall within the small margin area, then those examples you are quite likely to predict differently if you get a slightly different training set. Okay, so those examples you're not confident about, but luckily in this case you don't really have too many of those examples, and so on most of the examples you can be very confident. If you had a lot of examples right in here, then you wouldn't have large margin. So why are the large margins good? Let's stop here, and I'll continue in the next video. See you then.